Yep, so previously we ended with the shear stress, okay? And before we go on to talk about example 1-1, I'd just like to highlight a bit on the dynamic viscosity and kinematic viscosity. Okay, from the notes you'll actually realize that the kinematic viscosity units is meter square per second, right? And dynamic viscosity is Pascal seconds, or another way of expression is kilogram per meter second. Okay, so one interesting fact that I thought you might like to know is the two words, dynamic and kinematic. Okay, some of you may remember formulas like B equals to U plus AT, right? And I think S is equals to UT plus half AT square or something like that. This is in fact for formulas for velocities, acceleration, and time. And you will realize that over here is always about meters and seconds, okay? Length and time. There's never a mention of mass, okay? But if you look at dynamic, okay, the typical dynamic equation is your force equals to mass times acceleration, F equals to ma. Okay, here straight away you will see that there is actually a mass component here. So the one way of remembering is that these two words, kinematic usually does not have the mass component, while dynamic is about mass related terms over here. Okay, another interesting thing is that you can actually try to check it yourself that Pascal seconds actually is the same as kilogram per meter second. How do you do that? So let's say if I take pascals and seconds, right? So Pascal is what? Pascal is force over area, right? So Pascal is actually Newton per meter square times second. And you know that F is equals to ma. So what is the unit for Newton? Actually, Newton is actually also equals to kilogram for mass, and acceleration is meter per second square, right? So this is actually Newton over meter square times second. Okay, you can actually cancel out, and you will realize that you are left with kilogram per meter second. This is how you derive that they are indeed the same. Okay, so let's go to example 1-1. So you have two plates, right? Two plates separated by a layer of liquid with a viscosity of 1.55 times 10 to the power minus 3 Pascal seconds. So straight away off the bat, you see the unit of this viscosity is Pascal seconds. It means what? It means that the dynamic viscosity is given to you. Okay, so dynamic viscosity is 1.55 times 10 to the power minus 3 pascals second. Okay, the top plate has a constant velocity of 2 meters per second, while the bottom plate is stationary. The gap is 1.5 mm. Okay, so if I write in SI units, it's 0.0015 meters. Okay, and the area is 1.2 meters square. Okay, so how you draw the velocity profile? Although the question does not ask you to draw, you can draw it this way: u, y, okay, 0.0015, and this is 2. So this will be your velocity profile. Okay, this is how you draw. And how do we find part A, the shear stress between the liquid and the top plate? Remember that the shear stress, the value is the same, so we can find tau equals to mu du dy equals to mu delta u by delta y equals to mu u2 minus u1 over y2 minus y1. Okay, so we just put in the values. Everything must be in SI units. So this is in SI units. Okay. U2 is the velocity at the top plate, which is 2 meters per second. Bottom plate is stationary, so U1 is 0. Okay, the height at the top is 0.0015 and bottom is 0. So what do we have? Oops, sorry. I think this is correct. 2.067 pascals. Okay, so this is the shear stress. And determine the force needed to pull the top plate. Okay, it means that you're asking for the shear force. Okay, shear force is simply shear stress multiplied by area. 2.067 times 1.2 meters. So you get 2.48 newtons. Okay, so these two are the answers to example 1-1.